Social Brain. This is episode number 24. I'm Andrew Cooper Sansone. With me is my co-host Taylor Guthrie, and we are talking about memory today. Kind of the new understanding, the new neuroscience of memory. I think this episode is going to be really fun, really interesting, and I'll hand it off to Taylor to get us started.
Yeah, and we'll do a quick call out at the beginning. We're on episode 24 now. Thank you, everyone, for continuing to listen and to support us. If you can help us out, joining our Patreon, you can do it for as little as $1 a month. Every little bit kind of helps us and keeps our motivation up to keep doing this. We love doing this show, but any little support helps. So let's dive in. So today we're going to be talking about kind of this new trajectory with thinking about memory, and thinking really in terms of what it is that the brain is actually trying to accomplish. If you really try to understand your mind, try to understand your brain, it's important to think about kind of evolutionarily what the brain was responsible for. And a lot of what we're going to be talking about today is about the brain trying to predict what's going to happen next. There's a lot of people that think that the brain is trying to understand the world, but when you really look at it, the brain is trying to move through the world. The brain is trying to understand what's going to happen next, what people are going to do, and all of these things. And I'm pitching all of this. I'm talking about the future, but memory is a huge component of predicting what's going to come next, because our brain is constantly trying to take all of these things that happened before. It's taking everything that's happening right now, and it's creating this model to try to say, like, okay, what does that mean for what's going to happen next? And there's this really fascinating research that we're going to get into today, where they've started to map out this kind of hierarchy in the brain to look at how memory may not be this thing that we maybe think it is, where there's maybe like a place where memory lives, but really memory is more of just this information processing kind of flow. And it's part of the brain just trying to understand what's happening now and what's going to happen next. So yeah, we'll kind of jump into it. And I know that was kind of vague, but we're going to get into the nitty gritty and really talk about how this is burgeoning as a new way of really understanding kind of where memory fits in the context of everything we've talked about.
Yeah, and I like your emphasis on that memory is for the future, which is like intuitively sounds a little weird when you first hear it because, well, memory is all about the past, what happened before. But of course, like Taylor was saying, our brains really evolved to efficiently move us through our environments and allow us to do things to survive and reproduce, and so having that store of information that allows us to better predict what the environment's going to be like, what we're going to have to do to get what we need to survive is really, one of, if not the evolutionary function of memory.
There's this fascinating kind of philosophical quote that URI Hassan uses. We're going to be talking a lot about his research today. He's one of my kind of favorite neuroscientists. But in one of these talks that he gave, he said, the current moment contains nothing but the past, yet it's constantly used to shape our current actions and to plan for the future. Right. And that's really interesting to think about kind of philosophically, right? Like the present moment is nothing but the past. When you think about how long it takes for this information to go through these processing circuits and everything, we're really operating kind of on in the millisecond level in the past in terms of the brain regions that actually constitute awareness. Some of the other brain regions, the sensory regions, they may be more in the present, but we, in terms of rumination, in terms of thinking, in terms of all of these things, we're actually operating completely in the past. And we're using all of that information to kind of create these models of what's going on right now for our current actions, but then how those current actions are situated in what we're kind of leading towards. And we've talked a lot in this show on these past episodes about goals, about goal directed behavior. And it's really important to think about organisms, to think about humans, think about all animals as constantly striving to achieve goals that can be physiological, food, water, safety, sex, right? But as humans, our goals are very complex. They can be very psychological, right? These needs to belong and to be recognized and to be creative and to do things, right? And our brain's constantly trying to work towards those ends. And it's using everything we've learned before, combining it with what's happening right now to try to figure out where we are in that kind of map of our goal space.
Yeah, and this is all a lot of information right up front, and maybe to help people kind of understand it and digest it, maybe we should step back and think
Yep.
about what was, the traditional view of memory, whether it still holds some weight or not, and how neuroscientists think about, moving into the kind of newer stuff. But let's, step back and talk about that more traditional view. And as you mentioned before, it's this really simplistic idea that you just have processing and memory in the brain. That you have like areas that do perception, that like perceive the world, take in sensory data and understand it, and then you have areas that store that information and then retrieve it for later use. And while there may be some, actually, I don't want to go into the caveats yet. Let's keep just going down what this traditional view looks like.
And I mean, think about where a lot of this started, right? A lot of our kind of intuitive understanding of the brain kind of mirrored where we were in terms of like computer science. That we started to create computers and we started to think about the brain in terms of a computer because it was the closest thing that we had to what a brain was. And so we created these things that had hardware components where you had this one part of the computer that did processing and you have this one part of the computer that saves all of the information, right? And it really influenced these models that were coming out in terms of trying to understand the brain in those ways that we're going to be able to find this like region where everything is stored, and then this other region like the frontal lobe that like accesses that and uses it to do all of these computations, and that really there, like Andrew said, there is some kind of link to that, but it's not very strong. And we're actually, now that computation is advancing, something we'll talk about kind of throughout the episode is that we're also learning a lot now from these new artificial intelligence, like large language models and things like that. And we're starting to understand that the brain might be a lot more like what we're kind of moving into now in the artificial intelligence world than what these kind of simple computer designs were.
Yeah, it's interesting how the progress of technology and computer science specifically can inform and also kind of delude the neuroscience of memory or neuroscience generally. But so yeah, so I think it's pretty clear, and maybe we don't want to give too many details on the traditional view because it'll confuse people. So maybe talking more about what is the difference between the traditional view and what we're calling this new science of memory. And I guess I would say it's more like the key word is distributed. The network or the memory, a memory is not just stored in one place, like put in a treasure box that you put in the attic and then go get it later to get the information out. It's more like it's in the very regions that were kind of processing that experience to begin with. So maybe we should dive
No,
into
there's
that.
there's a great quote that really encapsulates all of this, and it's that there is not a system of memory, there is a memory of systems. That the systems that you're using to interact with the world, to engage, to smell things, to hear things, and see things, those are the same systems that are being reactivated when we're remembering things. And as we get into this, a lot of this is going to get more clear as we get into some of the science that's unraveling this whole thing. But it's really about the process of memory is that we're reactivating those things to better understand the current moment. It's an information processing pathway. It's not that we're just like accessing this memory just to kind of like relive the old days or whatever, but the memories are being brought online because they have some kind of connection to what's happening right now. and what's happening kind of with our future goals and all of these things that are going on. And because of that, like all of these systems that are happening that are kind of controlling our movements in the current moment are interacting with other systems that were on in the past. And there's systems that are kind of integrating those together and comparing them and seeing what that can do to help us kind of increase our predictive power in the future.
Yeah, so maybe to make this a little more concrete, we could
Yep.
dive into some of Uri Hassan's work and talk about his really interesting studies looking at auditory stimuli and what that reveals about the kind of structure of memory or and processing really in the brain. Um, and I guess a key thing to keep in mind throughout this is there's really this blurred distinction between processing of stimuli like perceptual processes and memory, because like Taylor's saying, it's the same pathways that are processing stimuli that you're seeing in your outside environment are the ones that are changing, and that change is kind of a representation of memory in some way. And maybe I didn't say that
No,
precisely
no,
enough, but
no. I think it is important to kind of get into this because I think it's going to really kind of paint this picture. This is, I think, some of the most revolutionary neuroscience that I've ever seen. I mean, Uri Hassan is by far one of the most influential neuroscientists in terms of the way that I think about these things, in terms of the hierarchy of brain organization and all of these things. And it all comes back to one of his most influential studies. And so he is one of the pioneers in really changing the way that MRI research is being done. So a lot of MRI research in the past, especially with like memory and things like that, it was very static. It was that I'm going to show you a picture of two things and remember those two things. And then you're going to look at nothing for like 10 seconds. Then you're going to look at two new things. And then you're going to look at nothing for like 5 or 6 seconds. Then two new things. And that's how MRI research was done for 10, 15 years. And it's only been recently that we've started to use stimuli, so the things that we're showing participants in the scanner, that are more natural, because that's not how the brain interacts with the world. We're not just like seeing a ball and a rocking chair and being told to remember that the two things are connected, right? Instead, our world is naturally unfolding, right? It has a temporal component to it. And so he figured out ways to computationally look at naturalistic stimuli. And when I say naturalistic, I mean things that have more of a kind of natural basis. So having people listen to stories, to podcasts, to audiobooks, having people watch movies, and seeing what's going on in their brains as the brain is kind of tracking over time what's going on in that narrative, right? And what he kind of introduced was this new way of kind of looking across people, is the intersubject correlation, where you can take the same part of someone's brain and another person's brain, and you can see whether or not that part of the brain is doing the same thing in two people as they're watching this movie or listening to this story. And so what he did is he had this long narrative, this audio kind of podcast or whatever it was, and he split it up into a bunch of different conditions. So first, he played this whole thing backwards to people. And if you've ever heard like music, like a song played backwards, it's bizarre, right? It's just like a bunch of like random weird sounds, right? And so if you look across people, you say, okay, what regions of the brain are doing the same thing when they're just listening to these random sounds? And what he found was that the only regions that were having the same activity were the early processing regions, the auditory cortex. And the auditory cortex, all it cares about is sound, frequencies of sound, right? The auditory cortex is just kind of a map of high tones and low tones, right? And so across people, because they were listening to the same sounds, those parts of the brain were super in sync with one another. But then he played it forward, but instead of playing like the whole narrative, he scrambled it. So he just gave them just random words, just like the it, and and then yeah, and yeah, and so it's like it's actual words, but it's nonsense, right? It doesn't have any narrative structure to it, and so you don't have to track what's going on. You don't have to remember anything, right? And what he found was that you had the auditory cortex, it's just processing sound, but then you had like a little bit of spread of activation around that. that now you have regions that are recognizing that these sounds are words, right? It's putting those frequencies together and it's saying, okay, well, that was and that was like boat. Like, I don't know how those fit together, but uh, so then he had one more condition where instead of just random words scrambled, he scrambled it at the sentence level. So they heard a whole sentence. So, yesterday I went to the store and then this thing happened, but like the sentences they didn't fit together. There wasn't narrative structure. It was just a sentence. And then it was another sentence from like 5 minutes later in the story. Right. And what you see is you start to see the spread away from the auditory cortex, where now you have the sounds being put into words. And now you have the words being embedded within sentences, because sentences require you to track some type of structure throughout them, right? We have to make sure that there's noun verb agreement, that the prepositional statements make sense, that the grammar makes sense. And we have regions of our brain that are kind of tracking that. They're like, okay, we have these words, and now these words are being put together in a way that makes sense. But you didn't have any spread from that. And so this last kind of set of conditions that he had was that he scrambled it at like the paragraph level, and then he had people listen to the whole story. And what you see is now you have the sounds, you have the words, you have the sentences, and now you see this spread of activation into these really high order areas. Like we've talked in this show before about the default mode network, which is able to track information over really long time scales or whatever. That what's happening is that you have different parts of your brain are operating at different time scales. So you have the early sensory regions, so like the early visual cortex and the early auditory cortex. They're processing things on the order of milliseconds. They just care about sounds. But then this next region cares about the sounds that are happening now, but also the sounds that just happened a second ago, so that it can put those two sounds together into a word. And then you have this next one that's operating on the term of like a second and a half in terms of like a whole sentence, where it's not just tracking the sound that just happened, but how those sounds were put together into words, whether those words go together, whether they fit in some grammatical structure. And then from there, you have these other regions that are tracking the whole kind of narrative progression of this thing, right? The reason that I know what the word it means or what the word he means was that it was defined as Bob in sentence 1 3 seconds ago, right? And I have a part of my brain that's able to understand what's going on right now and what happened like 5 seconds ago. And it's able to integrate all of that information into the current moment so that I can understand the narrative. And the higher you go up in this hierarchy, because they call it a hierarchy, right? You have low processing, and then you have higher timescales and higher timescales. When you get to the default mode network, you're able to integrate over minutes and over hours, right? The reason you're able to listen to this podcast and listen to me talk about this study over the last 2-3 minutes or whatever is because you have a region of your brain that's able to listen to what's happening right now, but is able to also turn on all of that information that's happened over the last 4 or 5 minutes, right? And so it's integrating all of this stuff into a coherent narrative over time. And so when we're talking about memory as being an information processing pathway, we have to think about the fact that these areas that are at the top of the hierarchy, that are processing things at really long time scales, are able to listen to what's happening right now, but they're also able to turn on all of these old memories and able to understand what's going on and integrate all of that information into a whole.
And that's that blurred line between perception and memory, because you have to have that a certain kind of a certain form of memory. Working memory, or is not really the term that Hassan uses, but I mean, for our purposes, like it's this kind of recursive, like looking back on what just happened in order to process what's happening now. And that's an interesting flip from saying, oh, you perceive something and then you store it in memory and then retrieve it later. It's a much more integrated kind of system.
And it's happening in the moment, right? It's not that I'm getting to the end of the story and then I'm turning the memory on. The memories are on the entire time. I'm not just like turning it on at the end so that I can remember something. It's our daily existence as we're walking through the world. Even if we're not consciously bringing a memory to mind, we're using memory from all of our past experiences in similar contexts, in similar situations, similar social interactions. All of those are online while I'm interacting with the world, because they're being used to kind of facilitate my prediction about how I should act right now.
Right. And if it weren't that way, you wouldn't be able to recognize, for instance, objects, any kind of specific object in your environment. I could hold this up and you're not thinking like, oh, let me recollect what is that thing.
Mm-hmm.
It's not a conscious process. It just happens in that moment. And if there weren't this integration between memory and perception, and that presumably wouldn't happen as efficiently, that kind of thing.
And it's really interesting to think about kind of where this goes, because we're talking about this in terms of kind of challenging some of these previous views of memory. And Hassan really tries to understand, like, okay, we have this ability to track things over time. Um, and a lot of the studies that he was doing were about kind of this kind of 5-10 minute narrative, right? And so, okay, I see that the default mode network is able to kind of track this narrative over the last 5-10 minutes. But how does that explain how we remember things over years? How we remember things that happened a day ago, 2 days ago? We can be watching a show, right? And we can pause it at time point 33 minutes and watch the next half of it a week later and still remember what happened in that first 33 minutes, right? And so he did these really interesting experiments where he did that exactly, where he showed people half of a video, and then he had them come back a day, a week later, or whatever it was, and tried to see like what the difference was between someone watching it all the way through and someone watching half one day and then half like the next week, right? Um, and so many of you, if you've kind of got into like memory research or anything like that, probably have heard of the hippocampus. The hippocampus is really important for memory. And what he found was that a lot of the processing, narrative processing, is happening kind of in the moment. But if you need to activate things from a longer time period than like 5 or 6 minutes ago, then the default mode network is actually communicating with the hippocampus to turn these old kind of memories online. And that's what he found, is that this other group that had waited a day or two, that it was still the same processes were still happening in terms of like these high order default mode network regions kind of tracking the narrative. But then he found that there was this communication then with the hippocampus, and the hippocampus is this fascinating piece of machinery in our brain that has figured out how to reactivate these circuits that were active when we were doing things a week ago, a year ago, whatever it was. And you see this with lesion patients. So if you have someone that's missing a hippocampus, and we've had tons of cases of people like that over the years that researchers have spent tons of time studying with them, you can have a conversation with them, and they can track the whole conversation while you're having a conversation with them. But as soon as that narrative breaks, they lose it. And so there's something about like this in the moment tracking things, like keeping track of like the structure and the memory of what we're talking about right now. But if you have to bring on anything that was like 5-10 minutes, an hour ago, then there seems to be this connection to this other piece of our brain.
Yeah, and just to clarify, I think some people might think of the hippocampus, because of what you just said, as being, oh, well, that sounds like a memory storage center. That sounds like the hard drive of the brain. But like Taylor, if you caught what he was saying specifically, it's that it's reactivating memories that are in reality stored in distributed networks in the cortex. And then it has this function of taking these sort of shorter term memories and then somehow creating a kind of like a call tag so that it can find that more easily, or reactivate that memory more easily when it's actually needed. And we'll get into sleep in the next episode, but a lot of that process of communication between the cortex and the hippocampus happens while you're sleeping, which is why sleep is so important for memory. But I digress.
No, I like to think of the hippocampus as like our Google search engine.
Yeah.
Because you kind of you need the right search term to like turn on those things that we need. And this is kind of a just like an interesting kind of aside, but uh, there's some work that I did in my master's degree looking at kind of the emotional effects on memory. And it's really important kind of thinking about memory in these terms to understand that there are different types of memory, right? That depending on what circuits were active, we may have emotional memories, may have like action memories, right? Um, what the hippocampus seems to be really involved in is contextual memory. It's involved in, and if you look at kind of the connections that are feeding into it from like the parietal lobe down into it that are responsible for episodic memory, for us remembering specific things that happened, they usually are tied to a time and a place. And there's tons of animal research about the hippocampus that looks at its role in kind of navigation and kind of recognizing where we are in a particular place. When you're in a really traumatic event, when something really kind of high emotional thing happens to you, your body is flooded with cortisol. And cortisol, it's these glucocorticoids. The hippocampus has a ton of receptors for them that actually shuts down the function of the hippocampus. And so when you're in this really heightened emotional state, you're not actually laying down a bunch of connections to the context, to where you are, what happened. You're not creating a Google search term. And so what tends to happen with like people with PTSD and things like that is that they don't have the ability a lot of the times to like actively recall these memories by using like a time and a place. Like if I think about like, okay, what happened on my last birthday? I have this Google search term, that I have this time, I have this place, I can think about what happened, and then the hippocampus is able to like bring all that stuff online. Um, but if it wasn't online in those moments, then what's actually triggering those things is more of a similar situation. It's not the hippocampus doing it. It's more that like I saw the the uh, the fan going and it's like helicopter blades, and so there's this generalization function that all of a sudden turns on all these similar pathways to the one that I experienced. And so you're not actively turning it on like you would with the hippocampus, but your body is just reactivating it because of similar things that are happening. And that's kind of a I
Yeah,
digress,
yeah.
but
That's really interesting because something else that happens during stress is the activation of the amygdala, and the amygdala also has a kind of memory function built
yeah,
into it where it can sort of store these. They're probably like salience based memories, but they're going to or I mean traditionally looked at as like fear or aversive type of memories that aren't contextual. They don't have
yeah.
that rich context that the hippocampus does. They're more they're triggered by sensory events, and then they're not necessarily specific when they're reactivated, but it can just reactivate fight or flight reaction.
And I think that's important to highlight in terms of what we're trying to get across here is that the whole goal of bringing memories online is to process the information that's coming in right now, right? And so in some cases, it's important to have this contextual kind of connection to what's going on right now compared to these previous places that I've been, these previous like times in terms of like the time of year or whatever it may be, that may be kind of facilitated by the hippocampus. But there are other times where our brain doesn't really require that contextual information, is using different paths to reactivate some of these circuits. That may be threat circuits, that may be action circuits, right? But the whole point of bringing on old information is to kind of facilitate our current actions and to understand what's going on right now.
Yeah, yeah, and it's interesting to think of memory in that way. And I just wanted to also note that if anybody watching has any questions, feel free to drop them in the chat wherever you're watching us, and we will try to answer them to the best of our ability. But I just want to put that out there. We usually say that at the beginning, but anyway, where were we?
So I think something that's kind of interesting. I mean, I think this one is a little bit more kind of in the neuroscience nitty gritty, thinking about kind of the organization of the brain and how it kind of facilitates some of this stuff. Um, because what we're looking at in terms of this hierarchy, if you look at kind of these early processing regions, like the early auditory processing region, early visual processing region, structurally they're different than some of these other regions, like the default mode network and things like that. And Andrew hinted at something earlier in terms of distributed versus local processing. So a lot of these early regions are what are called like nearest neighbor processing. So there's lots and lots of neurons that are processing specific things that are maps of the world. So our visual cortex contains a map of the world where each individual neuron is mapping out a very particular area of space, right? But then as you move up the hierarchy, you're actually compressing all of that. You have a ton of neurons that are all feeding into one neuron. So in terms of like vision, let's think about like the process of creating a perception. You have a bunch of neurons that are just recognizing like edges and lines, and then they feed into just one big neuron that's reading from a bunch of them. That's like, okay, there's a bunch of lines. Those all together form this continuous line and an edge, and then those together form a corner. And as you go up, you have fewer and fewer neurons, but they're bigger neurons. They're these pyramidal neurons that are connecting tons and tons of these little ones from the early processing regions. And as you go up, you have just less and less that are processing more and more information. And you get away from the concreteness of this sensory stuff the further away you get. You get more and more abstract because it becomes more distributed. It becomes like you have less connections. You have these one neurons that are representing a whole idea, so to say. They found these in monkeys, right? There's certain complex visual cells that instead of just representing like a line or an edge, they represent the shape of a banana, or they represent the shape of a hand or the shape of a face, right? That as we move up, we start to see that there's just more and more abstractness. And you see this in gradients that we've talked about before in the show, in terms of like the frontal lobe. It goes from concrete to abstract when you move from the back to the front. And it also changes in structure. They call it agranular versus granular structure. And the granular is more of the kind of lots of little cells, and the agranular is more of the big kind of distributed cells. And I think the point I'm trying to get at with all of this is that if you have these really big cells at the top that are really distributed, that are connected to lots of different types of information, it gives them the ability to access different flows and different circuits, right? Because they have so many things feeding up to them, because they're the top of this pyramid, right? Think about the structure of a pyramid. You have tons of things at the bottom, then you have less in the next row, that less in the next row, but that thing at the top is able to connect to everything. And so in terms of reactivating memories, these things at the higher ends of the hierarchy are able to understand things that are coming up, that are on right now, but then they're able to turn on all of these other things that are also connected that may be similar to what's going on.
So
If that makes sense.
Yeah, and so there's these fewer cells that are integrating information from the lower levels of perception, the more fine-grained details, and then that being sort of representing a more abstract concept. And an example of this that I guess, I don't know if this is a little bit controversial, but the idea of a Jennifer Aniston neuron, the neuroscientist, Quiroga is his last name, but I can't remember his first name. He found evidence that when you were recording from individual neurons in the brain, that when you presented somebody with a familiar picture of a familiar person, or someone that they knew, like a famous person that they didn't personally know, there would be one neuron that activated most strongly, that was firing most strongly or the most rapidly to the presentation of that person.
Yep.
And not to someone else. And I think the interesting, the funniest part of this was like they did this with Halle Berry, the actress, and they showed, okay, so here's Halle Berry's face, and then this neuron fires, and then they're like, oh, but here's Halle Berry in the Catwoman costume, so you can't see her face, but the person knows,
That's Halle Berry.
cognitively that's Halle Berry, and that neuron was still the one to fire. So
even the word Halle Berry fired it.
right, yeah, that is good. Yeah. But I guess we should maybe distinguish that from the idea of a grandmother neuron, because now we're veering further into perception, but I don't know if we should
No, I think
clarify
that's
that.
totally okay, because I think perception and memory are intimately linked. I think that's one of the
Yes.
biggest points that we want to make throughout this episode, is that they're not separate. We're using our perceptions as a process of memory. I think one of the big debates with these like grandmother cells, Jennifer Aniston cells, or whatever, is that if we lose this one cell, then we lose Jennifer Aniston, or we lose grandma, right? And that's probably not the case, because we have trillions and trillions of connections, right? That's going to be the case that there's lots of cells at these higher levels that probably are able to integrate information. And so these studies, they were only recording from like 100 cells or whatever. If they recorded from 1,000, if they recorded from 1,000,000, they probably would have found thousands of cells that all were like Jennifer Aniston. But it's because there's something important about that feature, right? That we've kind of tagged on, like that's an important person. And so we have these circuits in our brain that are recognizing that that's someone that's familiar, that's someone that has done something that we liked, that was funny, that was something like that, right? And so our brain has developed a circuit around recognizing those people. There's a whole part of the brain called the fusiform face area. And it was called the fusiform face area because we recognized that it was really active for faces. And then there was this idea that like, oh, it just does faces. But then we found that it's also really active for cars, for people that are car aficionados. And it's really active for birds, for bird watchers. And so the whole idea here is that we are consolidating information in these circuits that are important to us. That when you think about this whole hierarchy, you have to think about bottom up versus top down processing, right? So a lot of what we've described right now has been this kind of bottom up approach. You have this visual stuff coming in, you have this auditory stuff coming in, it's feeding its way up through the hierarchy to the top end, and the top stuff is what's kind of understanding everything. But we have to think about the fact that the top actually has an influence on everything else too, that there is this kind of this reciprocal communication between them. And I think that's what's really going to lean into kind of the second half of what we're going to talk about today in terms of prediction. Because if you think about what we care about, right, the whole purpose of memory is to facilitate our needs. It's to facilitate us accomplishing things in life. And so the reason why there's circuits for Jennifer Aniston or for grandma or for whatever is because those people were important to us. And so there was a reason to consolidate and integrate and have circuits that were kind of connected to aspects of that person or that event or that thing. And the top is able to simulate everything that's happened on the bottom. It's able to turn all of these things on, right? We've talked previously on our show about visualization, that these top areas are able to turn on all of these things when there's nothing happening in the real world. And what we can do is, let's say that I was really hungry, right? And I really wanted an apple. The regions at the top are going to say, apple. I need an apple. And they're going to send that signal down to all these lower processing regions. And it's actually going to be easier to find an apple because those regions are going to be primed to fire more when an apple shape appears. And so that's where we get into this kind of predictive area, is that these higher order areas, they're really trying to facilitate future needs. They're trying to work towards and move towards things that we want and that we need. And they're sending signals to these lower regions to look for those things. They're kind of priming them. They're saying, this is the shape that I'm looking for. So if anything happens that's that shape, that's what I want. Yeah, go ahead.
Yeah, no, and just another example of that in the visual arena is like there's these studies looking at visual perception, and if I were to like throw a football and there was a barrier in front of where you like between you and I, so you couldn't see the ball going behind that barrier, you just see me throw it and then it would come out the other side. There are there's studies looking at early visual perceptual areas in that context. And because people know that it's a ball that's flying behind this barrier, there are cells that are firing as if they could see that ball going through space. So that it's like if there was a map of space and that area behind the barrier is occluded, your visual system nonetheless guesses, okay, this is probably where the ball is behind this barrier, and then it comes out the other side, and then normal perception continues. But it's this a process of prediction because we know what's happening. Our lower sensory areas, our early sensory areas, are predicting, are acting as if that we can see that thing to better predict what's going to happen in a second or two.
And so we have to think about where this goes. Like, how is this useful for us in terms of understanding? Okay, we have memory is not stored somewhere; it's a process. Great. Okay, it's predictive in nature. Okay, but think about kind of the power of this, right? Because we, in terms of awareness, in terms of what control our self has, is really in creating the value around what those predictions are, is creating the model of what I want, what I need, that is then tuning all of these other systems to look for that information. Right. And this is where, when you get into kind of learning and memory, you start seeing these effects around kind of self-enhanced memory. If something is self-relevant, it's really heightened in the brain. It's because of the fact that we're setting these top-down kind of projections in terms of, this is what I really want, this is what I want to see, this is what I want to do, where I want to go. And these top-down regions are then kind of tuning all of these lower perceptual regions to expect that, to predict that, to look for that. And then we're constantly testing those predictions by interacting with the world. And there's really interesting stuff that we've, I think, talked about previously on this on the show, in terms of like action prediction, in terms of so let's say, like Andrew was talking about, like throwing a ball. There are these really interesting studies where you put on like prism glasses, where it kind of shifts your your view so that you think you're looking straight, but everything is kind of over to the side. And so when you throw a ball at a target, you think you're throwing it at the target, but it actually goes like way over to the right. And what they've found is that the brain, it's predicting where the ball is gonna land when you throw it, right? It's creating this prediction, and then things happen, and then it's seeing that it was wrong, and it actually adjusts. So even though your vision is totally off, you're able to adjust all of your actions and hit the target. And then when you take the prism glasses off, you're actually off again, and you have to like readjust your prediction in your model. And it's really interesting how that all works.
Yeah, so there are these feedback processes between our prediction of what's going to happen and then what actually happens, and then that feedback allows us to like adjust that memory, that perceptual, or in this case, motor pathway, to take into account this shift. And I guess we're emphasizing that these kinds of changes happen most strongly when something is valuable to us, right?
Mm-hmm. No, I think so. Because that's where a lot of these models are situated, is within kind of the needs-based framework, in terms of what our goals are. That we're going to put a lot more action into correcting wrong predictions if it's something that is really meaningful to us. And this is in terms of any type of, like, if you want to learn something better, if you want it to kind of stick, then it has to be something that you care about, that you have to see kind of the end goal of what is it that this information is going to do for me in the long term, in terms of helping me to achieve my career aspirations, or helping me to achieve better connections with my loved ones, or whatever it may be. If you can situate whatever you're learning into one of your kind of important needs and one of your important values, then your brain is going to situate its predictive framework around those things, if that makes sense.
Yeah,
Sorry,
absolutely.
jumping around a little bit today.
No, yeah, but it kind of goes along with what we keep saying, that there's this blurring between I think not just perception and memory, but action and memory too,
Yep.
right? And how we haven't even talked about it, but how kind of the executive uh, regions of the brain, the frontal lobe specifically, has a really similar kind of processing slash memory hierarchy that goes from very concrete actions to very
Yeah.
abstract goals. But anyway, getting back to predictions, you were saying something. I think I kind of
No,
threw us
I
off the
no,
rails.
you're all good. I actually kind of like where you went because I think that there's something that we may have overlooked in terms of uh, anyone that's thinking about this is probably thinking like, okay, but there are kind of specific memories that seem to be stored somewhere, like episodic memories that we can kind of relive, and like how are those different than maybe memories that are about kind of abstract things? Uh, and I think that you were kind of getting at this idea in terms of like the frontal lobe and its organization, but really thinking about how the brain is trying to understand information on two different scales in terms of specific events, in terms of like general events or abstract events. And I think a really good example of that is to think about if I were to bring up the term like chair, what image pops into your mind? And for any of you, it's probably, we all probably have like a different image, but it's probably like the perfect chair or whatever. It's this prototype. We're not thinking about like every chair that we've ever sat in, which ones were comfy, which ones weren't. You can do the same thing with like spoon or dog, right? You're not thinking about all of the instances of those things. And you're thinking instead of this kind of prototypical or this average object of whatever it is. And that's really what I think a lot of these regions are doing. Are trying to create kind of abstract categories of things that we've seen hundreds and hundreds of times that are really meaningful to us. Whereas there's other circuits in our brain that I think are more kind of situated around remembering specific things. And you can see that there's benefits to both of them in terms of there are times where I just need general knowledge. Like I've been in this kind of situation lots of times, interacting with this kind of person. But then there are other situations where I'm like, I need to be afraid of this specific dog that bit me, and I need to remember this specific dog. Uh, and it's interesting because we've seen that there's actually circuitry in the hippocampus that's separate for these two types of information.
Yeah, and that does seem like the hippocampus is kind of the key structure when it comes to really specific memories, like episodic memories, like you're saying, memories of particular experiences that you had in the past. The hippocampus seems to be required not only for the storage of those instances, but the recollection of them. And it's also, I think, not coincidentally, like you were mentioning earlier, um, this really important region for navigating us for navigation through specific spaces. So there are these place and space cells in the hippocampus that are kind of keeping track of where we are in an environment, whether it's a room or an area outside or something like that. But it seems like it might be, I don't know if this, tell me if you think this is wrong, but that the hippocampus is kind of like it is crucial for episodic memory. And it like seems like the studies of people with bilateral hippocampal
Yeah.
removal are show that it is crucial for at least the majority of like recalling those specific kinds of episodic memories.
Yeah, no, I think that's what a lot of the research is pointing to, because there's still people that have bilateral hippocampus lesions still remember tons of general facts about the world, things
Yeah.
that they learned a long time ago. But in terms of like laying down new episodic memories and figuring out how to make these connections to reactivate these circuits, that's I think where a lot of the research lies. And uh, memory, I think one of the things about this episode is it's been a very kind of broad, encompassing episode in terms of trying to situate how we remember things, how we interact with our present moment, how we predict the future. There is a massive amount of research just being done on the hippocampus. Uh, Alzheimer's disease is, I think it costs close to $600 billion a year in terms of its impact on the United States alone, in terms of lost productivity, in terms of healthcare costs, caregiver lost productivity, and all of these things. That has been one of the biggest drivers of kind of uh, NIH funding in the United States. And so, just at the University of Oregon, there are tons and tons of researchers that have gotten funding just to study the hippocampus. Like it's, I think memory is one of the most like over studied things. And so I just want to like put that caveat out there that we have kind of painted this broad picture in terms of memory, but there's a lot of nuance into how all of this stuff works.
Yeah, and we got a question in the chat. Hippocampus, never heard of it, from Ryan Meerstead, who is reminding me that yes, there are labs specifically studying the hippocampus or some aspect of it, and I don't know, I won't say his real name, but Ryan Meerstead is one of them. So
Yeah.
yeah, there's a
No,
lot
and
going on at multiple various levels of analysis, whether it's molecular biology or it's computational modeling or it's cognitive neuroscience. There's like a lot to be understood about this one structure and then memory in general.
so, and I think an important thing that we can kind of end the show with is that we started talking about how a lot of our understanding around memory was situated and where we were in kind of the computer age in terms of different hardware and different processing systems and things like that. We're now starting to see that a lot of these new kind of AI models are really interesting in terms of how they learn. So there's something called an objective function. So any of these kind of network models, these deep learning models or whatever they have a goal, just like we do as a brain. They're trying to achieve something. And a lot of their learning is situated in terms of like I want you to learn all of this stuff to do something, to move through the world. And what they found was that these large language models, when they made the objective function prediction, I want you to predict the next word. And think about like your phone when you're like texting or whatever. Your phone's constantly doing that. It's predicting the next word that you're going to say. Uh, when they put that prediction as the function of like, I want you to try to understand all of these things in order to predict what's going to happen next, the learning rates skyrocketed. And it was one of these inclinations that really kind of highlights a lot of what we've been trying to talk about in this episode, is that the function of learning, the reason that we learn, that we kind of solidify these networks in our brain, is because we are trying to predict what's going to happen next. And that's really like in terms of trying to understand like how to improve your memory and like the importance of the self, like we've mentioned before. That's really where a lot of that is situated. You have to understand kind of what the goal state is. You're going to learn things if you have a really clear goal that all of that stuff is kind of pointed at and situated in, and that you're constantly trying to predict like, okay, I want to become a something. And you're constantly trying to predict like, okay, well, if I do this, is that going to give me a leg up? And if I do this, is that going to help? Those kind of things of constantly thinking about those sub goals and those short-term things is really what's going to facilitate your brain putting more and more emphasis on solidifying the circuits that are involved in whatever that kind of thing is.
Yeah, I mean, I kind of think back to like college or high school and think about the classes that I took that had nothing to do with my major. Like I was a biology major, and I remember taking a British literature course, and I don't remember like anything from it. I think because at some point halfway through, I was like, nope, this is not what I'm going to be doing. This is not for me. And I think my brain was just like, okay, let's just get this information in, regurgitate it, and then never call on it again because it's useless. Not
uh,
to denigrate any English majors out there. It's too hard for me.
I mean, think about the most common question that like a high school math teacher gets, right? Like, when am I ever going to use this? Uh, and a good teacher is going to have a good answer to that. A good
On
teacher
the
is
test.
right, yeah. But I mean, that's how so much of academia is situated right now. Is that most of your learning is learning that's situated around that short term goal. And so a lot of it is just memorize and regurgitate. And none of that really sticks in terms of like setting down these really concrete circuits that you can reactivate, that you can use, that you can have a conversation about and really kind of understand and express that you understand to someone. That's only going to happen if the information that you're learning has some impact on what it is that you're doing, right? So for me, like, my best learning happens when I have to teach something, because the goal state is really that like I have to understand this well enough to like tell other people, to talk to other people about this, right? It needs to be solidified in a way that I can in the moment I can reactivate all of these circuits, that they're part of this information processing kind of hierarchy. um may have been a little all over the place in today's episode, not our our most organized one, uh yeah, it's one of those things that if you have a strong enough goal, if you have a strong enough kind of end state for any of these things, like you can get there. Yep.
Yeah, exactly. Ryan in the chat says, if you can understand it well enough to teach it to someone else, that's a whole new step of knowledge. That's so true. And
Yep.
I think something else that relates directly to what we are talking about with the distributed nature of it's like abstract conceptual memories in the brain is that there's this idea in the psychology of learning and kind of like learning theory that there's this strategy called interleaving, which is this idea that what you're learning, you should try to kind of integrate it, like interleave it with other things that you're trying to learn. And that makes the most sense of like if you're a student in school and you're learning, calculus, but you're also learning physics. Like, okay, how do you? Those are two obvious ones that you can kind of fit together, and that maybe that has to do with kind of linking up these higher
Yeah.
order networks, these abstract conceptual networks, and that leading to a stronger recall ability, a stronger memory in the future. So, that's another tip you can kind of walk away with this understanding of how these memory systems in the brain are distributed, is that if you can integrate what you're learning, what you're trying to learn with what you already know and see, oh, how does this new thing affect what I already know about everything else or about some other specific thing that you're learning, that can help to kind of solidify this memory.
Yeah, the most effective teachers I ever had made a habit of linking current topics to things we previously learned. So you're onto something there. Yeah, I think, and think about, and this is kind of speculative. This is abstract, but think about what Andrew was just saying in terms of. I spend a lot of time lately really thinking about kind of the structure of knowledge uh, in terms of neurons, right? These like trees of neurons that are all kind of interconnected, right? Uh, there's something when you look at kind of language in general, there's this idea of spreading activation, that so if I put the word hair up on the screen, you would probably think of like hair. But if I put a picture of a rabbit on the screen and then the word hair, then you probably think of the rabbit hair. And it's because of this idea that I'm kind of spreading this activation. I've kind of started this circuit about a rabbit, and now all of the words that are associated with that kind of come online. And so when you're thinking about what Andrew just said, if you're able to connect these disparate ideas together, you're actually connecting these like webs together. And the whole thing about this top-down control of these things, that these areas at the top of the hierarchy have the ability to reactivate stuff. And so if they're reactivating one thing, but that thing is connected to other things, they're really reactivating this entire kind of branching web of information, that in the moment you now have access to this whole kind of repertoire of information, that is all kind of interleaved and connected, that you can call on, that's primed, right? It's an interesting idea.
Yeah, and then this relates to another like extremely effective strategy, learning and I guess memory strategy of just practicing recall. because you need to strengthen those pathways that you're forming in the process of learning. When you're learning, oh, this idea connects to another, this is what this is. It's not just that you have to form those networks, but you have to strengthen those pathways, and especially the kind of ability to recall it. So some of the most effective learning strategies are just testing yourself on your knowledge without looking at the answer. And that's been shown like over and over again in the psychology of learning. So again, and that's kind of neuroplasticity at work. You're building stronger connections within these networks, and then also kind of to sort of output them.
There's a really interesting addition to that comes up in my group dynamics class. So we're really good. I mean, what's really important in terms of like studying with other people is that you need to kind of have some kind of understanding yourself before you go and kind of interact and study with other people, because there's actually this facilitative effect that when we're around other people, it actually makes us better at the things that we're already really good at. And so if you spend this time kind of learning these things and like integrating them, then all of a sudden you're in this social environment. And think about what we were talking about in terms of like goals and needs, that you have this need to not be embarrassed, to not be like, to not kind of look like an idiot in front of these other people, right? And that actually causes you to have more emphasis on strengthening these connections. But it's actually been shown that if you don't do the work of trying to understand those things first, it actually makes you worse. And it can kind of be a detriment to learning, because then you end up embarrassed, and then you end up in this kind of threat cycle and these things. But it's interesting kind of situating in terms of like needs and things like that. LTP induced with flashcards. Yes.
True.
True.
Yes.
So I think we're about time.
Mhm.
Thank you for sticking through with us on this one. I know it was a little jumbled, but I think there's good tidbits here and there.
Yeah, and we will be back. The next episode will be on sleep, and we'll kind of cover some of the memory enhancing effects of sleep. So look out for that. And I'll just flash our QR code again here. If you guys want to help us keep the lights on and support the Social Brain, you can go to patreon.com/thesocialbrain and choose whatever level of support you want. As little as $1 a month. We would really, really appreciate it. That helps us to keep this going, to kind of justify the time we spend here, even though we love doing it. It's we need to pay the bills as well. So it looks like someone scanned the QR code,
Yeah.
told me. So that's awesome. Thank you to whoever did that.
Appreciate that. And look out too. So we're in the process of kind of creating some cool merchandise. We have really cool kind of brainy images that we've created, and our official logo that we're going to put on shirts and stickers and mugs and all kinds of cool stuff. So we will have that soon.
Awesome. All right. Well, thank you everyone for watching. Thank you, Ryan, for all the activity in the chat. And yeah, I hope to see you soon. But have a great rest of your week, everyone.
Yeah, thank you.